welcome to my short tutorial on working with remote sensing data in Earth Engine. Who am I? Should you listen to anything I'm saying? Well, hopefully. I have a master's in Earth Observation and Geoinformation Management from the University of Edinburgh, where my thesis focused mainly on Sentinel-1 star to understand the backscatter pattern of surface lake development on ice shelves. And then since I graduated, I've worked at Fauna and Flora International for just over a year in the analytics team. So I've built up quite a bit of experience working with remote sensing data, and I work across many fields in FFI. But as I said, I mainly focus on remote sensing, GIS, data viz, and geostatistics. And there's a picture of me on top of a hill in the Peak District, but I mostly spend time at my desk, so it's almost a lie. And I'll just quickly go over what I'll cover in the next half an hour. We'll start by getting acquainted with the Earth Engine platform, and for those who are unfamiliar or are beginners. And then we'll have a look at what kind of data sets you can access, how to access them, and how to view the metadata associated with those data sets. And then we'll start our Earth Engine experience by creating a cloud-free Sentinel-2 mosaic with quite a short reproducible script. And then to finish, we'll visualize a Landsat 8 image in false color and also calculate NDVI of a Landsat image and make a chart of this. So that's the raster interpretation and visualization. And hopefully after all of this, all the scripts I've written, I will be able to send out as a link so you guys can copy and play around with the scripts and kind of have a go yourselves at what I've done. So what is Google Earth Engine on this extremely loud slide? It's a solution to the problem of having to download and store huge loads of satellite data. It can eliminate this aspect of remote sensing work and gives your computer a bit of a break by doing those heavy tasks on Google servers. It's a really, really flexible platform with a huge amount and variety of data available that can be applied across a really wide range of research areas. And whilst Earth Engine does work in JavaScript, don't panic. You don't need to be a whiz at programming to be able to follow along. I'll cover a bit of the JavaScript language before we get started, but it's quite an explanatory language, and hopefully you'll be able to understand what the commands mean as we go along. And Earth Engine has facilitated long-term global research, and it's enabled researchers to analyze terabytes of imagery without the computational effort. And a great example of this is the Hansen Global Forest Watch data that we all know and love. Started here, and then 3 million Landsat images later and counting, we have that Global Forest Watch that informs so many people on tree cover, deforestation, and their ever-expanding list of variables. So now that we know kind of a bit about Earth Engine and how it works, we can have a look at the code editor platform. So the code editor platform is kind of the main area that you'll be working in, and you can access it via that link at the top, or you can just Google it and it will pop up. You do need a Google account to access this, or sign up for a Google account, so you can just log in with your Gmail if you have one. And we'll just quickly walk through the different aspects of the Earth Engine platform. So firstly, where the big number one is, we've got the search bar. And this is where we can search for all the data sets that could possibly be available to you. And you can also search places that will pop up on the map. The box number 2 is filtered by 3 different tabs. So the scripts tab hosts basically where you write all your scripts and save them and organize them into folders. And there's also some examples in the scripts as well that you can follow. In the docs tab of that box, you actually have a list of available functions, their definition, and the requirements to use them, which is really handy to have that right as you're writing your script. And if you forget, you can look it up, or if you need to know something as you're going along. And then the assets tab basically holds anything that you upload to Google Earth Engine. So you can upload shapefiles, you can upload rasters, but anything that you have that's personal, you can upload it via the assets tab. And then number 3 is your script editor. And this is kind of where you concoct your potions. All the Google Earth Engine scripts are written in JavaScript, as I said, and they are performed by clicking run. There is no autosave on Google Earth Engine. You have to save manually. But even though when you close a tab, it will say there are unsaved changes. So don't worry, you're not going to randomly lose stuff, but save regularly is my main tip for that. Number 4 is our other sort of like, these are sort of our output area here. So you have the inspector tab, which shows our interaction with the map, so you can identify certain points. So you can get like a lat long by clicking on the inspector tab, and you get a crosshairs cursor, and you can click that way. And then the console is where your print functions appear. So anything that you want to write out and want to actually see, like an image collection or a table or a chart, will appear here. Your error messages also appear here. And then in the tasks tab, this is where you queue your exports ready for download. This is not automatic. You need to click run to actually export them to an asset or to your Google Drive. Earth Engine is kind of a lazy software. It won't really do anything unless you explicitly say, do this. So you need to click run and you need to make sure you click print if you want to see something appear. Number 5 is clearly the map canvas. All the visualization that you spatially you want to see will appear here. And you basically get the standard Google Maps base map and the satellite one as well. And then if you see the hand, the pin, the line, the shape, and the square in the top left corner of the box 5, this is where you can pan, you can add points, draw lines, polygons, and rectangles here directly onto the map for importing into your script. And we'll look at a direct example of this later. So now that we kind of know what Earth Engine is and we've got a good idea of what it looks like, we can start actually understanding what kind of data sets are available to us via Earth Engine. So Earth Engine has an entire data catalog, which, as it states, includes a variety of standard Earth science raster data sets, which you can import into your script with a single click. It's really easy. It's got hundreds, if not thousands, of data sets that you can access. In the catalog, you can search for a particular data set and enter keywords like country, feature, or type, like DEM or land cover. And all the data is tagged with several tags, so you can also browse by tags at the top if you're looking for something but you're not really sure what the word is you need to search for. And the 3 most popular data sets, Landsat, MODIS, and Sentinel, are listed at the top for really easy access to view all the collections associated with those missions. So we'll have a look at Landsat 8. So as we can see, the data catalog page for Landsat 8 is pretty full. We can see we're given information about the mission, the processing tiers, which is really useful for people who are using Landsat for the first time. And we're also given the option to use surface reflection, top of atmosphere, or the raw images, which is really great for beginners and experts who know a bit more about remote sensing and want something really particular. So Earth Engine doesn't limit you in any way when it comes to providing data. It provides huge information as well, also on the derived data sets for Landsat 8. So you can save yourself a whole lot of time pre-processing the data by simply accessing the derived data sets already done for you, which is great. And it also has a range of temporal resolutions from 8-day to monthly to annually. So you can see here on the actual catalog page that you have information on the data availability. So you can see that Landsat 8 spans from 2013 to 2020. You get information on the data provider, and you also get this Earth Engine snippet, which is what the description was referring to before, when you can import these to your data set with a single click. You can either copy and paste that image collection to your script and define it as a variable, or you can click that little box with an arrow and it will pop up a window ready imported in the script, ready for you to get started. And as you can see, there are all the tags available, so you can, this is what defines the image when you're searching for it by tags in the data catalog. And there are also description boxes, which gives you information on what the data is showing, as well as the bands and the image properties, and also gives references as well. So it's really informative for people who are getting started in remote sensing and want to learn a little bit more. Even if you decide not to work in Earth Engine, it's a really good place to actually find a synthesized information on the data sources. And Earth Engine is really, really great with providing examples at almost every opportunity. So it gives you a really quick example here on how to visualize a Landsat image collection that you can just copy and paste and have a play. You'll find that there are absolutely loads of resources, guides and tutorials for Earth Engine that are on YouTube if you like watching videos, or step-by-step tutorials online. But you're not, optical satellite data is the only thing that's not the only thing that's available to you. You can get C-band SAR. You can also access global land cover products, and for example, the MODIS burned area pixel product, all with example scripts and dataset information to get you going if you need it. So now that we've seen the data catalog, we can kind of have a look at something else that Earth Engine offers, which is the Data Explorer. So this is basically the web interface to Earth Engine, and you can visualize any data from the data catalog here. And if you're signed in, you can also import data and run simple analyses and export the results. So if you're a bit scared of the coding aspect of this, you could start here and work your way up if you fancied it. So now that we kind of know about the data, we can start coding. But as I promised, I will quickly go over a bit of JavaScript syntax so that everybody can follow along what we're talking about in the next few slides. So var signifies the creation of a variable or a function. So strings are marked with quotation marks like hello world, and integers and numbers are good on their own. Also, each line of code should end with a semicolon as well, I'll just quickly say. But if you forget one, don't worry, the code often runs without, but it will remind you that you need to put a semicolon in. And print tells the computer display the variable or string. So as we say, if we said print greeting, it would print the variable greeting, which says hello world. And 2 forward slashes signify that the following statement is a comment. So anybody that's familiar with coding knows that you should fully comment your data, so explain what every line of code does as you're writing it. And you can highlight several lines and click Control / to highlight them all, or I think Command / on a Mac. So you can define a list by using square brackets, and then you can create an object or a dictionary using curly brackets. And you can query this dictionary by referencing the dictionary name and the field in which you want to retrieve information from. And use the keyword function to define a function and its parameters. So you would include the list of parameters, as many or as little as you want, the statements that you want the function to carry out, and then what you want the function to return, and followed by a reciprocal curly bracket and a semicolon. I will say that Earth Engine works in American English, so make sure you're careful of your spellings. It will just spit up an error, but it's easy to fix. Okay, so now we're ready to do a little bit of coding. And we'll start off easy by creating a Sentinel-2 composite. And a cloud-free composite of a satellite image can come in really handy for almost any research purpose. But obviously, in extremely cloudy areas, you might have problems with creating a median pixel value, and finding a lot of cloud-free imagery might be difficult. And also, you should be quite considerate of seasons or temporal changes in your landscape when making a composite, so that you keep your images within the same season and you keep your pixel values relatively similar, so you don't have, if something is, for example, if something is deserted in in summer and rainforest in winter. You don't want to composite those together. So to start creating our cloud-free composite, we need to define our study area. So we can do this either by uploading a shapefile via our assets. So that's this form here. So you'll click upload and you'll choose your source files, and you can upload it as a zip or all of your files separately. You choose the name of your asset, and you can include some metadata here if you have a start time or an end time. And then you'd click upload and it would appear in your assets, and you can import it using this code at the bottom here by importing a feature collection and the name of your asset. But similarly, you can just draw it on the map. So this is what I've done. I've drawn a square in northern Liberia using the rectangle tool here. But if you have something that is a little more unique in shape, you can use this shape tool here. So I'll go through line by line of the code to kind of hope that everybody can follow along a little bit. So as you can see here, this is my commented out target features code here that, because I've drawn the geometry instead. So firstly, we will center our map on our focus area. And we will draw the AOI if we have imported it via target features. And then we can query the Sentinel-2 collection. So what we're doing here, and I'll explain it, is this is our Sentinel-2 surface reflectance imagery. And here we are filtering it by the cloudy pixel percentage. So we want really, really clear imagery, and we're filtering it by the date. So we're choosing the first half of 2020 here, and we only want the imagery that will sit inside of that green box we saw on the previous slide. So you can have as many or as little filters as you want on your query. It basically depends on what you're looking for. And then we can print this collection, and this will show the list of images that have been found that fit this query in the console. And that looks like this. So you can see the image collection here that we've defined. We can see that it's found 26 pictures that fit this query that we've we've asked Earth Engine to find. And we can actually view each of these images individually and have a look at all of their image details. And if you wanted to actually just look at one image on its own, you can just select one of these and import the image on its own. So next, to get an accurate mosaic, we need to reduce the images to bands of pixels in a stack of layers, and then find the median value of all these pixels to get a replacement for any clouds in the imagery. So we then divide by 1,000 to ensure the values between 0 and 1, and then we can visualize the natural color image using the natural color bands. And then we can save to drive here, or you can save to assets. So export.image.to-drive will send it to Google Drive for download, and export to assets will put it in your assets tab that we looked at before in the Earth Engine code editor. And as you can see here, we're selecting the bands that we want. This is the file name, the scale is the resolution of the image, and the region is our geometry. So this is what it looks like in the tasks tab. So you have this image that we called Sentinel-2 Liberia, and you have to click run, and it will run on the servers and upload your image to Google Drive or your assets, whatever you specified, you can choose here. And you can choose your folder, and you just click run, and everything happily sends it off to the Google Drive, and you can download it and have a look at it in, say, a GIS software if you wanted to. And our image looks something like this. As you can see, it's not entirely perfect. It probably needs some refining, as there are some sun streaks on the image, but you know, overall, it's a nice, clear, cloud-free composite of our target area. So now that we've covered this, we can have a look at a little bit more of our Landsat visualization. So we can load in our desired image. So you can either flick through a previously queried image collection like we did before and choose one there, or you can get the path in the row you want and format your image that way. So we can see here that I've picked a particular image that sits over Cambridge on the 25th of July 2019. And you can find a path row information at this link. Hopefully, if I can share my script, you guys can look at that link as well. And you can define how you want to visualize this satellite image. In our case, this is false color. So you just select the images that you want. There are loads of band combinations for Landsat. You just take a quick Google and you can find something different if you want to have a quick look at an image that way. And then we can use map.setCenter to Cambridge, and we can add our image and our visualization parameters, which we've defined up here. And we can call the image false color composite. So once we've run this script, we'll have something that looks like this in the map, which is the really lovely, clear false color image of Cambridge and of the rest of the UK as well. So it's really simple to visualize satellite data in Earth Engine. It's just a few lines of code to have a look at something and to see satellite data in any way that you might find useful. And we'll go a bit more complex now, and we'll head into working on an NDVI of a Landsat 8 image. And what we'll first do is define our area of interest. As we did before, we're using our square over Liberia, and you can use a point here or a polygon or a rectangle, whatever you've uploaded you can use here. And we'll import the Landsat 8 image collection. We're using the top of atmosphere one. And we'll use this piece of code to look within the Landsat 8 collection within the dates that we've specified here. So we're looking at the entirety of 2020, and we're going to sort this by cloud cover. And we're going to use dot first and empty brackets to pick the first image that comes up in this list. So we'll pick the least cloudy image of this list. And then we'll select the bands from our image. So that's band 4 and 5, red and near infrared. And we'll calculate NDVI using the usual equation, and we'll rename this new band to NDVI and then display the resultant image using this. But a really handy tool that Earth Engine provides is the .normalized difference tool, because Earth Engine knows that people that want to do remote sensing or regularly do remote sensing are always calculating normalized difference, and in doing this it simplifies your code from 3 lines to 1, and that's really beneficial in keeping your code reproducible and simple. So you can use this instead, and it will, if you just pick the bands, you can work with this in your image. As you can see here, we're using NDVI, and we are visualizing these, and we've again set our visualization parameters. We're going from red, yellow to dark green for our NDVI visualization, and we want to display our NDVI image using our NDVI parameters, and we want to call it NDVI image, and we're using map.addLayer. And this is what it looks like. You can obviously change the palette to fit whatever you find easiest to interpret, but it looks pretty to me. So what if we wanted to calculate NDVI over a series of images and not just one? So to do this, we will create a function. So we will create a function called add NDVI, and the function takes the image and performs the normalized difference tool on it using band 4 and band 5, and returns this image with the added band of NDVI. We'll test this on a singular image to make sure it works, and it does. I won't show you the messy testing process, but then we can add it to our entire Landsat top of atmosphere collection. Here we are going to use lowercase map, not uppercase map here, which is easy to get confused, but map empty brackets or lowercase applies the function to every element in the collection. and is not going to use the actual map canvas in doing that. So use capital M map if you're going to add a layer. So as you can see here, and lowercase map when you want to perform a function on an image collection, for example. And whilst it won't run all of the images on your map canvas, you can use your image inspector and it will show all of the NDVI images that you can access here, and you can work on individually if you wanted to. So here we have 151 elements, and we can use all of these. So what if we wanted to make a chart of NDVI over time, and how it's changed in our area of interest? First, we need to cloud mask though, so we can avoid having a noisy time series. So we'll make a function called Cloudless NDVI. And here we can see that we have using that dot mapped function again that takes and the function takes the image, and it's performing these three statements on the image that is run through this function. So we can see here we're getting a cloud score. We're masking all the cloudy pixels with a value of 20. We're computing NDVI using that dot normalized difference function that we looked at, and we're returning the image with the added NDVI band and updating the mask. And then we can print our chart using this. We basically use a print command and our chart from our image series. That's essentially what this piece of code means. And we're going to use the image collection of Cloudless NDVI. We're using the Landsat 8 collection. Our region is our area of interest, and our scale is 30, as Landsat is 30 meters. And that's our title is Cloud Masked NDVI over time. So here is our resultant graph. It's pretty nice. Obviously, you can edit the axes as you please, and you can also kind of use this piece of code to apply to many other different indices if you wish, and apply it to lots of different applications. Although I'm not sure what the issue is here during 2019. I didn't have time to investigate, but maybe someone could tell me what happened here with the NDVI values that year. But yeah, I'm hoping that fit the time. I think I'm a little bit over, but thank you for listening. I'll try to answer any questions that anybody has. But there's my email if you have a question you'd like to discuss more in detail. So yeah, thank you.
All right. Great job, Hattie. Thank you so much for that. That was a great talk. I see we've had a lot of questions in the chat about whether or not we will be sharing this tomorrow. And the answer is we always share all of our Tech Tutors recordings the day after the posting, sometimes even the same day. It just depends when we get to it, but it will for sure be up and you can catch up at any time. So now we're going to move on to the Q&A. You can keep asking your questions in the chat as we go if you think of anything, or you can drop them directly into the data wrapper notes, which are, I think they were just shared in the chat, but here they are. So we are going to, one other thing, if you are asking a question in the data wrapper, let us know if you have a mic so we can hand it over to you to ask the question, and turn your video on if you can during the Q&A, because it's really nice to see people interacting. And with that, it looks like our first question is from Joshua, and it looks like you do have a mic. Joshua, do you want to kick it off?
Yes, and thank you for the nice talk, Hattie. So my question, which I believe in the data wrapper, but I'll ask again for everyone's purpose, was what is the highest resolution, spatial resolution, open source data that we can use within Earth Engine? Because I know Landsat is limited to, I believe, 30 meters. So is there anything of higher spatial resolution that can help us work with smaller length scale problems?
Sentinel is, let me just check. I'm pretty sure Sentinel 2 is about 10 to 12 meters resolution. So that's probably in Earth Engine, that's the lowest I think you can go. In terms of actual open source, you can get archived spot data, which is about, I think it's about 4 meters resolution that you could potentially import to Earth Engine if you wanted to.
Okay, so the 10 meters is about the lowest without having to import your own data.
I think so on Earth Engine, yeah.
And then Dan Morris says there's NAIP, which I think is the agricultural data set, but it's only for the United States at 1 meter.
Yeah.
I think it's not native to Earth Engine yet, but hopefully they'll make
it
that
is on,
available.
It's on Earth Engine.
Oh, it is?
Yeah.
Oh, awesome. Cool. Thank you.
Okay, our next question is from Andy, and it looks like you also have a mic. Andy, are you there?
Yep. Hi. Thanks for a nice workshop. It's really nice to just see a quick rundown. It was a quick question about the Sentinel-1 dataset and whether there's whether you happen to know whether it includes both the vertical VV and the cross-polarized datasets in the assets that are included on Google Earth Engine.
Yeah, I think it does include all of the polarizations. Yeah, it does. Obviously, that depends on area. I don't think like Antarctica only has one polarization. But yeah, it does have all of the polarizations. There's HH, HV, VV, and VH.
Great,
Hope that answers your question.
It does. They must be coming from multiple places, but I'll dig into it further. Thank you.
Okay, our next question is from Carly. Carly, I know you got the answer to what NDVI stands for, but would you like to ask any follow-up questions about it?
Yes. Lots of people were saying NDVI, and I was trying to think of intelligent things that it could stand for. What it actually is was not on the top of my list. So is it just like a measure of, like forest cover or like plant vegetation cover, basically?
So it's kind of it's calculated from the visible and near infrared light reflected by vegetation. So you basically, maybe it's best I'll put a little graphic in the chat, but basically, so healthy vegetation reflects more near infrared than unhealthy vegetation. So you can kind of spot let's see if it'll send. So if you look at the graph, you can, or the figure, you can kind of see the difference, so that you would be able to see the visualization of the healthy vegetation that reflects more near infrared compared to the unhealthy vegetation that reflects a higher level of red.
Just to jump in, Hattie, do you want to just share screen for a sec to show that graphic?
Is it not loading?
Oh, no, it is just for the benefit of the video. Won't share the chat.
Yeah, I will. Let me zoom in on it. It's super small. Okay, here we go. So can you see? Oh, let's see. There we go. So you can see here, healthy vegetation absorbs most of the visible light that hits it and reflects a large portion of the near infrared light. Unhealthy vegetation reflects more visible light and less near infrared. So you can see here how a visualization of how it would reflect, and by calculating the ratio of NDVI, you can understand here. So as we see here, so this is near minus red and near plus red equals 0.72. So you can see the healthy vegetation has a higher NDVI, and the unhealthy vegetation following the same ratio as a lower NDVI. So then when you visualize this like in Earth Engine, for example, you can see that if I bring up my slide, you can see here these yellow areas have a lower NDVI compared to this dense forest here. Does this make sense?
Yeah. Yes, thank you. That is so like desert would just show up, like no vegetation would be just like yellow. And I work in a rainforest, so that's
Yeah.
like a montane rainforest area, so I don't, yeah, I'll have to play around. I'm interested to play around with it, but thank you. That was a very lovely description for someone who, yeah, I don't know, maybe that's like common lingo, but I'm very new to remote sensing, so thank you.
I hope I helped other people on the way as well. Usually if one person asks, everybody is thinking it as well.
Okay, so now we are entering the Rob block of the Q&A. We've got 3 Robs in a row. First is Rob Appleby. Do you want to take it away?
Really? Is it me first, really?
It is. You're the first Rob.
Wow. So I have a very basic question about, I've been interested in, I don't know anything about anything that's been being discussed, but I like the pretty maps and they're very nice. But could you, is it possible to describe or show the difference between, like, you were talking about resolution before, and 1 meter resolution to me sounds really fine scale. Is that true? Like, what does 1 meter versus 10 meter versus 100 meter actually look like, if you wouldn't mind showing that? And great talk, even though I know nothing about what you said. Thank you.
Yeah, so essentially the resolution refers to the pixel size. So I'll share my screen again, just because I feel like diagrams are always a really great way of explaining something. That's the true geographer in me coming out here. So so you can see this. Oh no, wait, you can't. Hold on. Here we go. So you can see this graph that is describing the pixel size here. So with a really useful house. So 30 meters here, a house is within 1 pixel. And you would have a 5 meter resolution here would be, the house would be split up like this, and 1 meter is even finer. And you can see the output display here. So you can see that the house would take up the majority of the 30 meter pixel. So the color of the house would be the main color of the pixel. And if you had a 5 meter resolution, it would be split more evenly. So you would get the rough shape of the house, and then a square of, say, if that was a garden, you'd have a green there. And 1 meter is much finer, where you can actually, you would be able to detail the exact boundaries of the house, and maybe features like a car or plants in the garden, for example. So a 1 meter resolution is super fine. It's not necessary for all applications. Sometimes 30 meters is absolutely fine. It depends on the scale that you're working in. A big protected area, for example, you'd probably be fine with 30 meters. But if you were, say, I know some in my master's degree, someone did an analysis using high resolution imagery to look at roofs in Africa, and replacing those roofs is an indication of a recent fire. So they would look at the reflectance of the roofs, and that would require really high 1 meter resolution imagery. But if you're just doing a large protected area land cover analysis, you probably only need the Landsat or maybe Sentinel for a higher resolution. Does that help?
Yeah, that's awesome. I have a lot of questions about resolution, which I won't ask, but yeah, that was very helpful. Thank you.
Great.
Okay. And Rob, if we have time at the end, we'll circle back to you for your resolution questions, or you can ask them in the after show. Our next Rob is Robert Klein. Are you still here?
Yes, I'm here. Thank you. so I am interested in the in looking at prairie dogs colonies in a desert, basically. So I pulled a Sentinel-2 image down, and I haven't worked it over with machine learning. I'm trying to figure out how to do that, basically. There are a number of problems with it in that there are a number of features around, like roads and buildings and whatnot, that the machine algorithm would have to learn, and I'm looking at a large area. So the question is, if I go through all this and identify all the areas for the machine learning, will I be able to discriminate between areas that are impacted by colonies versus normal desert or semi-desert, semi-arid desert vegetation? Is 10 meters a good enough resolution to do that? And some of these colonies are extremely large. They take up, 400 acres, and some of them are 30 acres in area. So that's what I'm trying to understand how to do. So the question is the discrimination in a semi-arid desert good enough to discriminate between areas that are impacted and those areas that are not?
Well, I guess that mainly depends on how well you've trained your model in terms of picking out the areas that are impacted by the colonies and areas that aren't. And you could have a play around with potentially emphasizing this difference with certain indices that might bring out the areas that have been impacted in a way that is more noticeable than the arid areas. So like for example, I'm just picking an example, on the false color composite, you can kind of see agricultural fields more noticeably than say like a woodland or something like that. So you could use an indice or an NDVI where it's picking out forest and unhealthy vegetation, and use that to emphasize the difference between the affected areas and the unaffected areas. And then that would help your machine learning model be able to pick out the difference by having a more distinguished difference between the affected areas and the unaffected areas.
Okay. So the best way to do it would be to walk it and map it with the GPS and then apply that to my Sentinel image. Is that make sense?
Well, yeah, you could do that and get ground truth data. That's always really useful to have. But from a remote sensing point of view, you could perform a calculation on your Sentinel-2 image to enhance the difference between your arid and affected areas. And that way it will help your machine learning model to differentiate between these areas, and having the ground truth data as well to be able to distinguish these areas will be really useful in telling your model this is an affected area and this isn't, and areas like this should be picked out, for example.
Okay. And if I had an area of, say, 3 kilometers by 3 kilometers, what percentage of the area would I have to map out to be able to predict the rest of the area? How many of those colonies would I have to march out?
So what I would probably do is draw a grid on your image and work through and kind of get an even number of points across each grid so that you've kind of got a fair distribution. If you work entirely in one corner, it will work great in that corner, and then it might not predict great for the rest of your image or area. So it's best to have quite an even distribution of points from across your area to be able to get an accurate prediction.
Okay, great. Well, thank you so very much for answering my question.
Thank you for asking.
Okay.
Okay, and
hang on, Ellie, let me just jump in for a sec. Robert, you might just jump into the chat because Andrew, it sounds like you should have a chat to Andrew because he's got direct experience about the questions you were asking.
Okay, thank you.
No worries.
Okay, and we've got the third Rob up now. I see you're already here, so go ahead.
Hey, Harriet, thanks for this super interesting call. I'll try and keep it condensed. I primarily work with ArcGIS, and I do a lot of like LiDAR collection and processing in ArcGIS, but actually the physical collection of that LiDAR data isn't in the like Esri. And so I'm wondering, does Google Earth have capacity, like does it store LiDAR data, and would it be worthwhile to pursue like automated, extraction of LiDAR and then processing? And then the second question is, are you aware of scripts that can assess diversity in tropical forests? A separate question, but basically just kind of picking your brain here.
Okay, so the first question with LiDAR, at the moment, I think it only works with like DEMs resulting from LiDAR data. I don't think you can actually work with raw LiDAR data in Earth Engine, unfortunately. But I'm not entirely sure. And secondly, you're asking about tropical forests and diversity, right?
Yeah, yep. I've done a good amount of research into different models for assessing tropical forest diversity, but I was wondering if you're aware of like scripts that exist in the platform already, or like potential avenues to research that further for Google Earth Engine.
Yeah, so I mean, I'm sure there is. I've not worked with any, but there are loads and loads of resources that do. If not, I imagine someone that has written a paper on it would be probably willing to share their Earth Engine code with you in order to do your results, I think. Sorry, I can't give you any more info on that.
That's perfect, thanks.
Okay, and next it looks like we've got Josh. Is this the same Josh that we had at the beginning, or is this a different Josh?
This Josh doesn't have a mic.
Okay, I will go ahead and read this one out. Oh, right, it says no mic. Okay, so different Josh says, does experience/knowledge of GEE translate to other similar systems? For example, do others also use JavaScript?
So JavaScript is really useful to just knowing language, even if you only know it in the Earth Engine, capability. It will help you learn other languages as well. Also, I think JavaScript has several like spatial modules for like web mapping and plotting through JavaScript in there. I'm not massively competent with JavaScript. I've mainly only used it in Earth Engine. For like spatial analysis outside of Earth Engine, I tend to go for Python or R. I find that to be a little bit more usable, especially Python. I think it has a lot more capability. So I haven't used JavaScript a lot, but I have used it for web mapping, which it was really useful for.
Okay, great. Next we have Sophie, and it looks like you do have a mic.
Hello, everybody. Can you hear me okay?
Yes.
Great, good to see you all. Thanks so much for the session, super valuable, really appreciate it. I just have a question around what species can actually be identified in 1 meter, sub 1 meter resolution. So we're talking 30 centimeters or 50 centimeters, so high resolution imagery. I've seen something on the chat about prairie dogs, and Dan mentioned the fact that if you can't see it with your human eye easily, you're not going to be able to see it with satellite data and be able to do machine learning on that to call out those species. So I just wondered how advanced this kind of species classification is from space, and who's doing what, and are there any kind of open source classifiers that could be used for high res data?
Yeah, so in terms of being able to track species from space, for high resolution imagery, I guess applies from any resolution, as we were looking at before in that little graph. If it's bigger than the pixel size, you should be able to, like an elephant is obviously bigger than 30 centimeters, so you'd be able to pick it out in a 30 centimeter resolution image. I know of the British Antarctic Survey have done whale tracking from space, which is really cool. In terms of open access, I'm not entirely sure. I guess it's more just a machine learning model. So you'd be teaching the model to pick out, say, if we use the British Antarctic Survey example, picking out whales in the ocean and learning to pick out that the black whale from the sea, and then tracking them that way, and then tagging that particularly unique whale and monitoring it over several images to look at the migration. So it's as complex as you want it to be, and using imagery. I'm not sure how advanced that technology is in Earth Engine. You might have to explore other options, but I'd say that was probably all the information I have on it at the moment.
Thank you for that's a great start. I'll keep researching and see who's doing what and what we can find. I'll join the remote sensing group. So thanks, everybody.
Just to comment, there's been quite a few suggestions in the chat as well, so, and some helpful links. So do check that out as well.
Thanks, Steph.
Sorry, my mute button was stuck. Okay, and it looks like we have time for one more question from Philippe. Are you here? Do you have a mic?
Do you want to just read out Felipe's?
Yeah, I'll go ahead and read it. Okay, so other than Landsat and Sentinel data, is there any other data set available on GEE that could help to detect deforestation at early stages and small forest fires as part of an early warning system to complement on-the-ground enforcement done by local communities in tropical forest in the Brazilian Amazon?
Yeah, so the MODIS, I mean, MODIS is pretty coarse resolution, has a burned pixel area. The Global Forest Watch data does have a global fires data set. In terms of the data available to you via Earth Engine, Landsat has, it depends how far back you are looking. I guess if you're complimenting people on the ground, Landsat has a burn area index data set that is available to you via the derived data set section of Landsat 8. So you could use that, and that's 30-meter resolution. If not, you could use the Sentinel-2 imagery, which is 10 meters, and use the burn area index calculation on that imagery yourself. And the collections on Earth Engine are kept pretty much near real time. So the latest Sentinel-2 image would have been collected probably, I can't even remember, this would have been yesterday probably. So you could calculate the burn area index, which is the red and near infrared bands, and use that on your Sentinel-2 imagery. It depends how small your fires are and how near real time you need the imagery. Does that?
Yes. All right. Thank you, Hattie. We do have one more quick question, if everybody's happy to hang around for one extra minute. And this one is from Marie. Marie, are you here?
Hi. Yep.
Yeah, go ahead.
Okay. My question is there a good place to share scripts or like import libraries? And is there some sort of community around this?
Yeah, so there are several communities. I think I linked on my Tech Tutors page that there's like a Google Earth Engine Reddit, and there's a huge community on Stack Overflow where you can ask questions and discuss with other people about their scripts, and you can suggest answers and that way. And in terms of sharing your scripts, I'll share my screen right now. There is a really great way to share your scripts. So here you can see this get link. So this get link gives you a link to your script that you've written, and others can access your code and run your code. Obviously, if you've uploaded anything that's unique to you in your assets tab, you will need to provide them with that data as well. But if you're just using collections from Earth Engine, you will be able to share this link and be able to run the code. Anybody else will be able to run the code as well. So that's a really handy way of sharing your work if you're working with a lot of other people as well. As I said, all of your functions are listed here as well, and you have a whole load of examples that Earth Engine provides that you can copy and use as you figure your way around Earth Engine. There are loads and loads of examples here, seasonal temperatures, elevation and temperature. So to get started, it's really easy, and there's lots of resources right in the code editor, and you are really easy. It's really easy to share your scripts as well.
Awesome, thank you.
All right, and we are on the hour. It looks like some other people have asked some follow-up questions and things like that. You are welcome to hang around after the episode. We do tend to stick around for an hour or so afterwards for a casual chat and for some extra questions. But if you have to go, thank you so much for attending. Also, register for next week if you would like to join us for our third episode this season, which is going to answer how do I use pattern matching analysis to label acoustic data with, I'm going to butcher this name, RFCX Arbimon. Steph, is that close at all?
So it's Rainforest Connection, everyone.
Rainforest Connection.
It's just
everyone.
a nice little, yeah. It'll be a really nice acoustic session about acoustics and analysis. So we've organised these first three to be around data and data sharing and data analysis. So we thought they'd link up quite nicely.
Yes, so thanks everybody. It was good to see all of you, and I hope you will come back again next time.
Thank you so much, Hattie. That was awesome. See you all later.
Everyone.